Hey everybody, welcome back to another video lecture. In this chapter, chapter 18, we're going to explore carboxylic acids. Um, we'll see how to name them, we'll see some of their physical properties, we'll talk about some of their characteristic reactions, and we'll look at how they are soluble in water and react with bases the way that amines reacted with acids and were also soluble in water. Remember, water can be an acid or a base, so the same thing happens to the molecule when it dissolves in water as when it reacts with either an acid or a base, depending on if you're an amine reacting with an acid or if you're a carboxylic acid reacting with a base. Okay, so let's just jump right in. So carboxylic acids are another class of organic compound containing the carbonyl group. So remember, the carbonyl is that C double bond O that we see not only in aldehydes, which have a hydrogen on the end, and then this could be the rest of the molecule, but also in our ketones, where, let's explicitly show our carbon here. Now remember, this is a polar group, so these had higher boiling points and melting points than regular alkanes and even regular ethers, because the CO bond is not quite as polar as the CO double bond, especially because of the shape here too. There's a few different ways that we represent the carboxylic acid group, or the functional group as we call it, the carboxyl group. So if I misspoke before, carbonyl is the C double bond O, and a carboxyl is what we call the whole grouping of the C double bond O with the OH on it. So again, when there's a C double bond O with an H, we call it an aldehyde. When there's just a C double bond O and two carbons, it's a ketone. We haven't seen amides and esters yet, but we will. In fact, I think in the next chapter we take a look at those. And hydrides, esters, and is it amides, or there might be a different one? Amides might get its own chapter. We will start to replace this OH group with things like a nitrogen in the case of the amides. And this is, again, attached to this C double bond O still. Or we'll, in the place of an OH, place an O something else. So that could be carbon. Well, it's going to be carbons, but it could be one carbon or a chain of carbons. We'll call these esters. And hydrides are where on that C double bond O, we have another O carbonyl group. So these are all the different things that can attach to the red carbon here. And we'll look at those in the next chapter. And again, all of these are groups that are still being attached to this guy. You'll notice in the case of anhydrides that we end up with two of them, one over here and then one here. Okay, so just trying to get you guys familiar with looking and recognizing carboxylic acids. Let's talk about nomenclature. Now for IUPAC names, the International Standard Naming System, for an acyclic carboxylic acid, we're going to take the longest carbon chain that contains the carboxyl group as the parent alkane. So if we, let's say we have something like this. Now, we could conceivably start numbering this way, let's see. 1, 2, 3, 4, 5, 6. 4, 5, 6. Let's just give this one another one here. Okay, so I could actually number this as a heptane and leave all of this as a substituent, right? But that's not how we would name a carboxylic acid. A carboxylic acid is going to include the carboxyl part, and if you remember with aldehydes, that'll automatically make this carbon the number one carbon. The carbonyl carbon will be the first one we start counting on, and then you can see the alpha and the beta. Remember, we had some other names for carbons that were neighboring the carbonyl. So in this case, if we were going to name this thing, we would start with the longest parent, or the longest chain that contains the carbonyl. So that would be one. Oops, that's not the one. It would be 1, 2, 3, 4, 5, 6, 7, 8. So we would get what would be an octane. We'll drop the E to form from the parent name, and we'll add oic acid. So octane will become octanoic acid. Now, if there's a substituent on there, then we'll have to number that and count it. In this case, that substituent would happen on the number 4, and it looks like it would be an ethyl, so we'd say 4-ethyl octanoic acid. So naming substituents doesn't change here. And again, we don't have to say 1-octanoic acid, because that's the only place we could put our carboxyl group. It has to be on the end. So in these examples, the common name is given in parentheses so that you guys can see that we do have common names that are not things that you would be able to puzzle out. So caproic acid, for example, or isovaleric acid. These are just names that people had named these particular substances, and so we can still call them that. They may be where they come from, or part of the process to extract these acids from natural sources. But in IUPAC naming system, we'll call this hexanoic acid because it's got 6 carbons. This one would be 1, 2, 3, 4, or 1, 2, 3, 4. It doesn't really matter. It's the same thing. So butane, so butanoic acid with a branch on the number 3, 3-methyl butanoic acid. If we were naming a substituent other than just an alkane, we could remember hydroxy is what we use for OH. Amino is what we'll use for NH2. Nitro is for NO2. Keto, right, for our ketone groups. Anyways. 5-hydroxy hexanoic acid. So this is just a variation of that. I'm here with a benzene on it. We'll call this guy benzenoic acid. It's benzene with a carboxyl group attached, and it doesn't matter where it's attached. That'll always be the number 1, and then we could number accordingly to get to the amino, or remember when there's 2 groups, we could say things like ortho, meta, para. Ortho means right next to it. Meta means 1 away from it, I guess, and then opposite sides of the ring would be para. If you were to encounter a dicarboxylic acid, then we would add the suffix dioic instead of just ethanoic. It'd be ethandioic acid, trioic acid, and so forth. To name the parent cane, when you have to name that, which you won't ever have to do it, there's also some other little rules to help make the name make sense. So sometimes, like the parent alkane name has an ANE, but it would become an ANE dioic acid. I don't know what I'm trying to tell you. You don't have to worry about naming those. The number of carboxyl carbons are not indicated because they can only be at the ends of the chains. So we don't need to say 1,3-propane dioic acid. We all know, or we would know, that we can't have a carboxyl group somewhere inside. So propane here tells us there's 3 carbons, so it's going to be on the 2 ends. Now there could be branches, you could have branches that also have, carboxylic acids, but again, you would try to find the longest chain, and then you would name this as a substituent, though we're not going to go over naming them as substituents. A few examples here, though. Pentane dioic, butane dioic. You can see some of these have common names you may have heard of. And then just to give you a big list here. So as the names get longer, you can see the formula just adds 2 carbons at a time. And there's a reason for that. When these carboxylic acids get made in nature, they're made biologically, and they get made 2 carbons at a time. When they're broken down as well by your body for energy, they get broken down 2 carbons at a time. They're little acetyl groups that come off. Anyways, so common names, you don't need to learn these, but you can see hexanoic, we said was caproic for caper or goat. Formic acid for formica, which was the word for ant, and that's what you actually smell if you ever kill any ants, or if you've ever smushed an ant in your fingers and got a smell of from what they usually use as a defense. They spray this formic acid out. Anyways, for common names, we use Greek letters and so forth to locate substituents. So you could, so you don't have to learn Greek for this, but alpha, beta, gamma is the Greek alphabet, and so the alpha carbon is just the one that's right next to the carbonyl, the beta, the gamma, and so forth. So if you wanted to, if you had a substituent that, let's say, was out on the 18th carbon, right, you could just find the 18th letter of the Greek alphabet and say it's that, whatever the substituent is. Maybe it's an amino group, butanoic acid or stearic acid or whatever. So sometimes that's the case. Now we also use omega, which is the end of the alphabet, to indicate where there are double bonds. So sometimes you have really long fatty acids, and they may be monounsaturated, meaning that they have one double bond, or polyunsaturated, meaning they have multiple double bonds. But sometimes it is designated as a omega-3, because if you start from the omega side, the double bond is on the 3rd carbon. So omega-3, omega-6, omega-9, these are common fatty acids that we find, especially in fish. Let's talk a little bit about the physical properties. So the carbonyl group contains 3 polar covalent bonds. There's the CO double bond. There's the CO bond, okay, and then there's the OH bond. All of these are polar bonds. So there is a lot of negative spaces on this molecule. You can see some negative spaces here on top of the carbonyl, some negative. And actually, what is happening here, there is some kind of partial double bond between these 2 oxygens, and sometimes these hydrogens will flip positions, or a molecule that has a hydrogen on it will lose it, right, to this acid, so that it can flip around. This double bond, remember, like in aromatic compounds, there's double bonds. If they can move, they will. And the fact that this oxygen has lone pairs and that it can drop a double bond down and these can pop up makes these guys pretty reactive as well. Okay, but also pretty polar. And so they are very soluble, or a lot more soluble than any molecules we've seen before. But it also is what's going to determine some of its physical properties, in that it will react really well with acids, it's going to be able to hydrogen bond, it's going to like water, and so on. So carboxylic acids have a higher boiling point than, like I mentioned, everything we've seen. Their higher boiling point is a result of their polarity, and the fact that the hydrogen bonding between the 2 carboxyl groups, or between 2 carboxyl groups, creates what we call a dimer. That behaves as a higher molecular weight compound. So when this molecule ends up sticking to itself like this because of the 2 hydrogen bonds, the carbonyl here is attracting a hydrogen bond from the other acetic acid, I think this is acetic acid, but the other carboxylic acid, and the carbonyl over here is getting a hydrogen bond as well, and so we get some sticking together, and so this makes it like it's just a bigger molecule. And so it takes a lot more energy to get this to boil or to melt. if you take a look here at some carboxylic acids next to just the regular, let's see, aldehydes, alcohols, and carboxylic acid. So aldehyde, alcohol, carboxylic acid. Molecular weights you can see are pretty comparable. Boiling point though of the carboxylic acid is much higher than even the alcohol compared to the aldehyde. And then same thing here. The aldehyde really low, a little higher for the alcohol, and then much higher for the carboxylic acid. So again, just that interaction between the carbonyl carbon and those hydrogens accounts for this. As for the solubility in water, as you start to get longer carbon chains, so like 5 and up carbons, solubility starts to go down. But as you increase more polar groups on there, then the solubility can go up again. But typically, if you've got just one, a fatty acid, so one side has that polar group on it, the longer the chain, the less soluble it'll be. But you can see here for acetic acid and propanoic acid, or acetic acid, I guess just acetic acid, with 2 carbons, it's pretty soluble in water. I don't have another list of propanoic and butanoic, but you would see the solubility start to decline as the carbon chain gets longer. Fatty acids are a derivative or a version of carboxylic acids. It's the version that we need to talk about because we're going to look at their biological relevance later on in the semester. Fatty acids are long-chain carboxylic acids that come from animal fats or vegetable oil, or phospholipids from the biological membranes that we use for our cells. There's been more than 500 fatty acids, types of fatty acids isolated from various cells and tissues. Most of these fatty acids have between 12 and 20 carbons. And they're even numbered, and I mentioned that. We'll see why when we get to the fatty acid synthesis and breakdown chapters. And in most unsaturated fatty acids, the cis isomer predominates. Trans isomers are actually rare. You've heard of trans fats, but trans fats happen due to a process. Let me actually show you. So here is a fatty acid, a sloppy one, and I'm going to put in a double bond. Now, when I show it like this is a trans double bond, and so like I said, these are rare. These form from when we have cis fatty acids and we try to reduce them using hydrogenation. So hydrogenation or sometimes partial hydrogenation results in the formation of trans fats. But a typical fatty acid then, if it has a double bond in it, is going to be cis. So it's going to look like that. So rather than be straight chained, which is what happens with trans fats, the cis ones add kinks. And these kinks to the chain are going to make it hard for trans fats to pack together nicely. Think about how nicely Pringles pack together in a can. That's what saturated fats do. They all look the same. They all pack together very nicely like Pringles. Trans fats can do that as well. Trans fats just aren't as good in our bodies, and for different reasons, and we'll talk about that later on in the semester. Cis fats, though, they can't pack together, right? The long kinks in the chain prevent them. Think of it like a bag of Doritos. These things rarely ever line up and stack up nicely, even though they may have similar shapes. They're just all pointing in different directions. That's what happens. And so when you start to put in double bonds into fats, and they start to kink up and not pack together as well, we tend to see them more liquid. They're in a more liquid state. Another way of saying it is that it lowers their melting temperature. They just have a lower melting temperature. So in room temperature, if you have fats that pack together really well, like let's say stearic acid, which is animal fat, no saturated, no double bonds, then this has a melting point of, let's say, around 70. So at room temperature, it's going to be a solid. But if we take something like linoleic acid also has 18 carbons. It's the same fatty acid as stearic acid. It just has some double bonds in it. There's actually 3 of them. And you can see here there's versions of stearic acid, oleic with 1 double bond, linoleic with 2, and linolenic with 3. Each of these with just 1, 2, or 3 double bonds changes the melting point from 70 degrees down to 16 degrees. So already at room temperature, this one's a liquid, -5 and -11 degrees. So at room temperature, all 3 of these are liquid, where this one's a solid, and they have the same number of carbons. This is because they don't pack together as well. And if they don't pack together as well, then they can't use those intermolecular forces that hold molecules together. The non-polarness or the polarness, none of that matters if you can't get close together to pack together. So sometimes a process that people do when they take saturated fats or oils is they hydrogenate them. Hydrogenate. So that means that they reduce the double bonds. They make them saturated. This often turns that into a solid instead of being a liquid. So margarine, which is sometimes just like canola oil, but it's been so somewhat healthier, right? Because it's oil. It's been hydrogenated so that it's more of a fat. Now that doesn't exactly mean it's healthier. Once you make it a fat, it's a fat. So is it healthier than butter? I don't know. Butter's a natural fat. This one's one that we made, quote unquote, in a lab by just hydrogenating an oil, which is normally healthier. But in my mind, once you saturate those bonds and you've made it a fat, that's what we're calling solid fatty acids at room temperature. We typically designate oils and fats, but they're the same molecules. Oils just don't pack together, and fats do. Once you turn an oil into a fat, it's a fat in my mind. But anyways, here we have some of those structures so that you can see, so I don't have to draw them for you. And then the saturated fatty acids, you can see they pack together really well, and that means that they have lots of intermolecular forces in between them. Now, granted, for non-polar molecules, it's just what we call dispersion forces. It's the weakest of all types of forces, but it's a force, and it's strong enough to hold these together, at least until the temperature is -11. Or in this case, 70, because this is the saturated version. Yeah. So all unsaturated fats are liquids at room temperature because they have cis double bonds that make it hard to pack. And oils don't typically come in just one kind of fat. If you look at the composition of anything, even safflower oil or avocado oil, there's usually a higher percentage of saturated fats, but there's always some amount of mono and poly unsaturated as well. And the opposite is true for animal fats. We tend to see lots of saturated fats and what did I say for oils? For oils, we see mostly poly and mono unsaturated fats with only a little bit of saturated fats. We see the reverse for animal fat. It's mostly saturated with only a little bit of unsaturated. Soaps are actually sodium or potassium salts of fatty acids. They're prepared from a blend of tallow and palm oils, which are triglycerides. Triglycerides are triesters of glycerol. I'll just show you. Actually, I think I have a molecule. So here's a triglyceride. If we go backwards, you can see glycerol. So here's glycerol. It's a 3-carbon molecule where each carbon has a hydroxyl on it. So it's a triol, 1,2,3 propane triol. But we call it glycerol. And when you react glycerol with 3, let's say, fatty acids, well, actually, yeah, this diagram is not going to show you guys what I want to show you. But when we have glycerol and 3 fatty acids react together, we can form a triglyceride. And we'll look at that reaction later on. A triglyceride is what we have in our bodies. And triglycerides are what we get when we eat animal fats. And triglycerides are how we store fats. But we typically break these down and swap out one of these fats, like one of these guys. We swap it out for a phosphate group, or we swap it out for an amino alcohol, or we swap it out for various different things when we put them into our cells. But anyways, we've got a glycerol, triglyceride, which is a way that we sort of have fatty acids, and the way we get them from animals. And what we do is we react that with, we used to call it lye. This is just sodium hydroxide. But anyways, the solid fats get melted with steam, and then the water-insoluble triglyceride layer that forms on the top is removed. And so if you wanted to make soap, so then that you take that water-insoluble stuff and you boil it with sodium hydroxide. And this reaction takes place in what's called saponification. It's Latin, saponum means soap. This was making soap. And so when you boil with potassium hydroxide, you get potassium soap. If you boil with sodium hydroxide, you get sodium soaps. We can use different kinds of soaps here. So this is a base. And what it's doing is it's reacting with essentially the fatty acid portions of the triglyceride. And what happens is it ends up breaking the molecule. So we get back an alcohol or glycerol, and we get back our fatty acids. But then the fatty acids undergo the reaction with the base, and they become the salts. So let me show you just how it's different. So let's just say this was the carboxylic acid beforehand, and this is it now. Okay, what's changed? Well, acids have hydrogens that they lose. So this fatty acid reacted with the sodium hydroxide, which is a base, to produce HOH, right? The sodium hydroxide provided the OH. The H here provided the other H, and then we got water. That's what acids and bases do. They react to make water. The leftovers now is this C double bond O with now a negative charge on this O. And then, of course, the rest of the molecule. This could have been 18 carbons. This could be 2 carbons. And so the sodium, which is now left over from our base, with its positive charge, cancels out the negative charge, and these guys just associate together as ions. This is how we make soap, and this is what soap is. And soap is really good at bridging that gap between oils and water, right? Because water doesn't dissolve oil, very well. But with the soap molecules, the long non-polar portion of it actually reacts with the oil and grease really well. And then the polar side, this little polar side here, reacts with water really well. It likes water. Water will surround it. And so this allows water to be able to scoop up oil because the water is interacting with the soap molecule, which has 2 sides. A side for water and a side for oil. It's actually pretty neat. So here's a different diagram. In water, soap molecules actually spontaneously cluster into these things called micelles. This is a 2-dimensional one, but if you can imagine a sphere, it would be a whole, a solid sphere of this stuff or whatever, of these little things all pointing inward. Ignore my picture. So a spherical arrangement of molecules such that their hydrophobic parts get shielded from the water and they all point inward, and their hydrophilic parts, the part that likes the water, stays in contact with the water environment, and then the sodium ions just float around. So yeah, these things form automatically, these micelles. This is what, and since micelles are actually just a simple version of our cells are a bilayer, actually like a double layer. This is a single layer, but the fact that these form on their own automatically is a good sign that life may have, been able to get started on its own at one point in the past. Though that'll probably be difficult to prove. When soap and dirt, such as grease and oil and fat, stains or whatever you have on your clothes or on materials, when you put them in water, and then you put soap in there, the non-polar hydrocarbon inner parts of the soap dissolve the non-polar substances. So the grease ends up finding its way inside these little micelles, just so it can be around things that are similar to it. And then the water continues to be able to wash this whole soap business off of your pans or off of your clothes. Now, natural soaps are actually... they actually form water-insoluble salts in hard water. So we end up with something called a soap scum. Natural soaps like this guy right here. If we react, we use something called hard water. You guys have hard water. Everyone has hard water. Usually for their laundry, especially coming out of their taps as well. We have ions. We have metals, safe metals, minerals inside our water. If you drink well water, you have hard water. There are things you can do to soften your water, but hard water usually contains things like calcium 2 plus, magnesium 2 plus, iron 3 plus. Okay, anyways, when that's present in your water and you use some soap, what happens is we get some ion exchanges, and the soap molecule here pairs up with the calcium instead to form something that does not dissolve in water. These things are typically insoluble, and so then they settle out as solids on your clothes. So we call that soap scum. This also happens just with water on its own. Water evaporates and leaves minerals behind on your faucets and stuff. But particularly when you add soap, and this happens, is when it's caused when it forms soap scum. So part of that problem in the formation of the problem with that hard water forming those solids was actually overcome by detergent companies by using a molecule containing a sulfonate group. A sulfonate is an SO3 minus group. These sulfonate groups in the place of the carboxylate group, so remember our carboxylate group is the C double bond O minus that we had on the soap, right? Calcium, magnesium, and iron salts of sulfonic acids are actually more soluble in water than the salts of the fatty acids. So detergent makers started making synthetic detergent, synthetic soaps. Well, it's synthetic because it's not made by nature. They call them SDS, a linear alkyl benzene sulfonate, LAS, and it's an anionic detergent. So you can see here they take like dodecylbenzene, they react it with some sulfuric acid to produce this guy. So instead of it being a fatty acid that contains this, which likes to react with things like calcium 2 plus and iron and 3 plus and all that stuff, they react with this part of the molecule to form soap scum. Instead, they have this to deal with. This looks something like this. Yeah, something like this. This, with the rest of the molecule like that. This doesn't react with these guys. So problem solved. I think I have, these are also some most common additives to detergents are foam stabilizers, bleaches, and optical brighteners. So you can see some of those structures here. They contain, this one has an amide, so it's a nitrogen attached to that C double bond O. Here we have a very unique looking structure, sodium perborate tetrahydrate. This is a bleach molecule. Again, you don't need to know anything about these, just some of the common detergent additives. Let's talk about the acidity of carboxylic acids. Carboxylic acids are weak acids. We can usually show those with a Ka or a pKa. Values of Ka for most unsubstituted aliphatic and aromatic carboxylic acids fall in the range of 10 to the minus 4 to 10 to the minus 5. So remember, Ka, if it's greater than 1, means that it is mostly favoring the this direction reaction, which means losing your H and looking like this and being acidic. The fact that 10 to the minus 5, right, or 174, is the number that we get. It's much smaller than 1. So the majority of this equilibrium lies this way, with these being the major molecules and only some of them looking like this. So these are not super acidic, but they are acidic. They do create hydronium ion in solution, right, by reacting with water. Just not to gloss over what I did here. Here's the carboxylic acid with the H. Here's a water molecule. These things will react to donate a hydrogen to that water molecule. Another way that we show this without the water molecule is we say we've got our acid and it ionizes. Right? That's what we get. We get it breaking apart into the two pieces. In reality, the water molecule's there, but this is what we're showing. So this is the acidity of carboxylic acids. Now, substituents of high electronegative, especially hydroxyl and chloride, here let me write these, hydroxyl, chloride, ammonia, with the plus charge. Whenever you have these things near the carboxyl group, it actually increases the acidity of the carboxylic acid. So, for example, both dichloroacetic acid and trichloroacetic acid are stronger acids than just phosphoric acid. Phosphoric acid, let me show you where phosphoric acid is pretty tough. It's a pretty strong one. Just to go back and show you, the lower the pKa, the better the acid. So phosphoric acid, which is H3PO4, has a pKa of about 2.1, and that's pretty low. Even though acetic acid here, right, has a normal pKa of about 4.76. Chloro, dichloro, and trichloro, look at that. Dichloro and trichloro are actually way stronger acids, even though they're technically weak acids, than something that we would almost consider to be a strong acid. And again, this is possible because of, let's see. This is possible because of the resonance of that structure, C double bond O. When we have this situation, let's say that we lose our H, so lone pair of electrons is still here, oxygen is now negatively charged. If this has the ability to move those electrons around, or to be more, what makes a good acid is how comfortable you are after you've lost your H. I think we've talked about this. Cl minus, when it's in HCl, I drew it backwards, I'm sorry, this is HCl. When it loses its H, it has 8 electrons, which is exactly what it wants. And so Cl minus is super stable. It doesn't go back and try to find that hydrogen again to form HCl. So when we say HCl goes into H and Cl, we don't even draw a backwards arrow. Cl is so happy that this is a one-directional reaction. In all of these that we're looking at, right, 2 directions, because this guy's not so happy. He's actually not that comfortable. It's slightly comfortable because I already told you that this has some resonance to it. This lone pair can drop down this way, form a double bond here, and kick this guy out, and have some kind of resonance. And that alone makes this thing a little better as an acid than it would be if it couldn't do that, because the more stable it is, the better acid it is, and this stabilizes it. Having something else that's really electronegative downstream from this molecule, or close to this molecule, maybe even like a dichloro. Remember, these guys are also very electronegative. So that means they're pulling electron density this way from the carbon, which means this carbon's losing electron density. So it's going to come this way too. That's more places for this negative charge to go. Rather than bouncing back and forth from O to O, some of that negative can come this way and stabilize this molecule. So that explains why adding more electronegative molecules to an acid ends up making it a better acid, but man, it makes it a really better acid. The acidity of carboxylic acids. When a carboxylic acid is dissolved in an aqueous solution, the form of the carboxylic acid that's present depends on the pH of the solution in which it's dissolved. So if you have an acidic solution, an acidic solution has a low pH or a high concentration of hydrogen ions. then we would expect that the predominant form of our carboxylic acid is going to have a hydrogen on it. It's going to be protonated. And when it's protonated, it doesn't have a charge. A neutral solution, we should expect sort of an equal concentration of the protonated and the deprotonated, or the what we'll call the conjugate base form of the acid. And we can actually call this something too. This is a carboxyl group. This is carboxyl, right? This is carboxylate. Carboxylate group. And when we are in basic conditions mean that we have high concentrations of OH minus. OH minus is going to pull off any hydrogens that are on any molecule that's acid. So we should find no acid molecules with their hydrogens still, predominantly the carboxylate ion. Let's see. And when you're naming, I forgot to mention, when you're naming these, we can actually name them as their carboxylates. So if we come back here, and this is let's call it what it is, ethanoic acid. This would be ethanoate, technically ion, because it's an ion. If it was paired with a salt, like when we were looking at soaps, I don't think we drew any good ones in here. Let's just say that this is a carbon, that this is that same molecule we're looking at. So 2 carbons, CH3, C double bond O, O minus, Na plus. This would be sodium, because we always say the positive charge first, ethanoate. Sodium ethanoate, because that's ethanoic acid. Ethanoic becomes ethanoate when it has the charge. You can see some reactions here. Benzoic acid with sodium hydroxide produces water, and then the sodium salt of benzoate, because benzoic acid became benzoate. Here, benzoic acid, which is slightly soluble in water, can also react with a weak base, like ammonia. This is a strong base up here, sodium hydroxide. But a weak base, remember, does the same thing. Ammonia, we saw in amines, will gain a hydrogen. When you gain a hydrogen in your ammonia, you get a positive charge. The benzoate still forms with our negative charge. And in this case, we get one of those polyatomic cations, ammonium. And we would call this ammonium benzoate. Let's do another one. So let's do this. Let's just have it be KOH, for example. Okay, so what is this acid? 1, 2, 3, 4, 5, 6. So this is hexanoic acid, and it's 1, 2, 3 methyl. 3-methyl hexanoic acid. We're reacting it with potassium hydroxide. So it's going to do that. CH3. So we get that guy. So the name would be potassium, because that's the metal, and then potassium 3-methyl hexanoate. 3-methyl hexanoate, because hexanoic acid, or 3-methyl hexanoic acid, was the name of the acid. Now that it's lost its H, it's just 3-methyl hexanoate. O8. Okay, so reaction with water essentially means it loses its H and it can dissolve. It forms its carboxylate. Reaction with bases produces a salt. So then you have to talk about the positive ion that's there paired with your carboxylate. Like inorganic acids, carboxylic acids react with sodium bicarbonate and sodium carbonate to form water-soluble sodium salts and carbonic acid. Carbonic acid then decomposes to give water and carbon dioxide, which evolves a gas. And so this is sodium bicarbonate here. And just you can see this is a carboxylic acid, reacts with sodium bicarbonate. Sodium bicarbonate is just like a weak base and a weak acid. It's kind of amphoteric like water. In this case, though, it'll react to donate a hydrogen to this guy, producing H2CO3, and it'll lose an H on this guy and pair up with the sodium. So that's why we see here sodium ethanoate, and then H2CO3 will decompose to give water and carbon dioxide. That's what carbonic acid does. Just as a third example of bases. Here I gave you a strong base, I gave you a weak base, and in this case, this guy is like I said, he's like an amphoteric acid or base. This is Fischer esterification. It's one of the most commonly used methods for preparing esters. We haven't talked about esters yet, but we'll look at that in the next chapter. An ester is when we stick an oxygen and carbon group onto our carbonyl carbon. So in Fischer esterification, a carboxylic acid is reacted with an alcohol in the presence of an acid catalyst, most commonly sulfuric acid, concentrated sulfuric acid. These are reversible. They also produce water, and it's possible to drive this in either direction by choice of experimental conditions. So if we want to, if we want to make lots of this ethyl ethanoate, then we just remove the water as it forms, or we use an excess of the alcohol to drive it forward. And if we wanted to, take an ester and break it apart, we just use lots of water and just drive the reaction backwards. So what you're seeing here is that the OH group from the carboxylic acid and the H from the alcohol will join up to make your water, and then we get a connection between that C double bond O and everything that was attached to it to the O and everything that was attached to it from the alcohol. So this is the alcohol part, this is the carboxylic acid part. So it's useful to remember that the O that's still on here does not still belong to that carbon. Now we don't need to go through the mechanism here. You've seen carbonyl reactions in earlier chapters. Nucleophilic attack on that carbonyl carbon to cause some rearrangements. In Fischer esterification, the alcohol adds to the carbonyl group of the carboxylic acid to form that tetrahedral intermediate. So I think you guys maybe remember that. Or no, actually we looked at a carbocation in the past, so maybe this one is a little different. So what happens is this O with its lone pairs comes in here and attaches, or it forms a bond to the carbon, causing the lone pair electrons on the double bond to kick up or to become a lone pair. So now that oxygen, now what will happen too is that this oxygen, once it sort of, we could, instead of saying that there's two steps where the electrons come up and then reach out, we could just say it's a rearrangement. The O switches being bonded to the carbon to grabbing one of those hydrogens off of the alcohol. So we get some group switching. We get a new bond forming here, and then we get a new bond forming here, and then eventually we're going to get the loss of a water. This intermediate loses an H2O to give an ester. And that could be this part up here once this forms to help, this bond get made, then the lone pairs come back down again, or actually a different molecule with its OH will probably, right, this is like another one of these, and this OH down here can be like this one, and it'll reach out and grab that hydrogen so that it can leave as a water, because waters are good leaving groups, reforming the carbonyl. Again, I'm not going to test you guys on the mechanism, but that's Fischer esterification. It's one of the main reactions that we talk about with carboxylic acids. Let's talk about decarboxylation. That's the loss of a carbon dioxide from a carboxyl group. Almost all carboxylic acids, when heated at very high temp, will actually undergo a thermal decarboxylation. And so you can see here, you'll lose a CO2. So whatever was attached to your carbon will gain that hydrogen, and carbon dioxide will be lost. Most carboxylic acids, however, are pretty resistant to moderate heat and melt and even boil without undergoing decarboxylation. So it's not super easy to make happen. An exception is any carboxylic acid that has a carbonyl group on the beta carbon. So let me show you what that looks like. So remember, here is our carbonyl carbon. The alpha carbon is next to it, and then the beta is one over from that. If the beta also has a carbonyl, right, we call this the decarboxylation of a beta keto acid, right, because this beta is essentially a ketone. The mechanism of thermal decarboxylation involves a redistribution of electrons in like a cyclic transition state, so like this, followed by two keto-enol tautomerisms. I don't remember if you remember that much from the keto-enol tautomerism from the last chapter, but followed by, so two steps, redistribution of electrons followed by the keto-enol tautomerism to essentially remove the decarboxylation. So it's a complicated little step, but it does happen. And an important example of decarboxylation is of a beta keto acid in particular in biochemistry occurs during the oxidation of food that we eat in the tricarboxylic acid cycle. We have this molecule oxalosuccinic acid. It's one of the intermediates of the TCA, the citric acid cycle. And it has a carbonyl group, in this case a ketone, beta to one of its three carboxyl groups. And so the formation of this molecule is important so that we can essentially breathe out the carbon dioxide or breathe out the carbon molecules that we are ingesting as sugar, right? Putting it through this cycle, making a bunch of molecules and then breathing out CO2s is how we use sugars and how we gain energy. But it's neat to see this in action, right? So here you have that oxalosuccinic acid. Here's your alpha, here's your beta, and then after that, you see, trying to see how we lost our CO2 here. We lose, we lost this CO2. This CO2 is gone. But we don't get the mechanism for that. I mean, the mechanism happens back here. You guys saw that. It involves some pretty crazy rearranging. But yeah, in this example, I guess we could say how do we know, or why didn't this guy leave and just this guy? Or how, or why? Here's a better question. The carboxyl group that leaves is the one that has a carbonyl group beta to it. Do any other of these carboxylic acid groups have a carbonyl beta to it? That's the question. So this carbon, right? This is alpha. This is beta. So no carbonyls. This carbon, this is alpha. This is beta, carbonyl. Okay, so this is the one that leaves. This carbon, right? This is alpha, this is beta, no carbonyls. So the only carboxylic acid group on this molecule that has a beta carbonyl to it is this group. And I guess this is saying it, but I needed to see it. So that's the one that leaves. It's the one that has a carbonyl beta to it to allow for this rearranging of electrons and then the tautomerism to happen. All right, guys. That does it for the carboxylic acid chapter. Again, we talked about a few reactions here. One that I didn't mention that's always important to note is that carboxylic acids, in addition to being able to decarboxylate, in addition to forming esters when we react them with alcohols, we got to remember that they can also reduce. You can reduce a carboxylic acid, platinum, palladium, nickel, some kind of catalyst. Carboxylic acid gets reduced back into an aldehyde. And if we further reduce that, we get a primary alcohol. So don't forget that important reaction as well. But in addition to the reactions, physical properties, and naming, don't forget about the solubility, which is physical properties. And I guess when I say reactions, I mean two with acids and bases, or with water, with bases, with the alcohols and the decarboxylation. Basically, the solubility, right, when they form the carboxylate ions. That part is usually tricky for students. So practice those, ionize them. That means write your acid, reacting in water, or just ionizing. Leave the water out, but show it getting its charge, losing its H, right? That's what ionizing means. This helps to explain why it's soluble. This helps to reinforce the naming. So when you name this one as an acid, name this one as a carboxylate. Anyways, all right, guys. See you in the next video.